Hey everyone, and welcome to this explainer. Today we are taking a seriously mind-bending journey into a microscopic world where the normal, everyday rules of physics simply break down. We're going to explore the universe of nanomaterials. It's a hidden frontier that is fundamentally challenging literally everything we thought we knew about the building blocks of reality. So get ready, because we're about to zoom in closer than you've probably ever imagined.
Okay, let's dive right into this. I want you to picture a block of gold. If you take that block and, say, chop it in half, well, it's still gold, right? It still shines like gold, it still melts at the exact same temperature, and it still conducts electricity exactly the same way. Even if you chop it all the way down into dust, it's just really small gold. But what if you keep chopping? What if you chop it down so impossibly small that the very nature of the gold itself begins to fundamentally change? That is the big question we're exploring today. Can the mere size of an object actually alter the laws of reality it obeys? Well, as we're about to see, the answer challenges absolutely everything classical physics has taught us.
All right, Section 1, Journey to the Nanoscale, zooming in from the familiar to the invisible.
To really wrap our heads around these counterintuitive rules of the very small, we kind of have to understand the sheer scale we're dealing with here. Let's move to and see how this builds. So think of a human hair. That's about 80,000 nanometers thick. Pretty small. But if we zoom way past red blood cells, past viruses, all the way down to the width of DNA at just 2 nanometers, we eventually approach the absolute bottom, a single hydrogen atom sitting at 0.1 nanometers.
So what exactly makes a nanomaterial? Basically, it's any material that has at least one dimension measuring somewhere between 1 and 100 nanometers. And just to put that into perspective, 1 nanometer is exactly 1/1000th of a meter. But you know, what really blew my mind isn't just that these materials are insanely small, it's that right within this very specific 1 to 100 nanometer threshold, materials simply stop acting like their normal everyday selves. Instead, they start exhibiting completely unique physical, chemical, and biological properties.
Section 2. Why size changes everything. The power of the surface. So, why does this happen? Why do the rules of reality just flip upside down? Well, it has entirely to do with the sheer power of the surface. Imagine a solid block of, really, any material. Most of the atoms making up that block are safely tucked away inside, right? Happily surrounded and stabilized by all the other atoms. But the atoms on the outside, on the surface, they're completely exposed. They've got all these unfulfilled connections and they are just desperate to interact with the world around them. Now picture shrinking that block down, down, down. As the object gets smaller, the ratio of its surface area to its volume absolutely skyrockets. By the time you shrink a particle down to just 1 nanometer, an astonishing 50 to 80% of its atoms are suddenly right there, completely exposed on the outside. There's practically no inside left.
And this brilliantly illustrates why things start getting so weird. Because of all those desperate exposed surface atoms, the material becomes incredibly reactive. It practically turns into a powerful catalyst. Its surface energy spikes so drastically that the entire structure becomes precarious. I mean, it literally melts at a significantly lower temperature than a regular-sized block of the exact same stuff. Plus, its adsorption capacity, which is its ability to grab onto other molecules, just goes right through the roof. Simply by shrinking an object, you are effectively turning it into a high-energy, hyper-reactive powerhouse.
Moving on to Section 3, the quantum confinement effect. When electrons get trapped.
But here's the thing. Surface area is only half the story. Down here, we also have to deal with the bizarre world of quantum mechanics. Let's keep this super simple. In a normal, large piece of metal, electrons are free to just roam around in these continuous bands of energy. It's kind of like they have a massive, wide-open highway to drive on. But when a particle shrinks down to the absolute microscopic extreme, specifically the size of an electron's actual wavelength, the electron suddenly finds itself trapped in a tiny microscopic box. Because the box is so incredibly tight, the electron can't roam freely anymore. It gets forced into these incredibly specific, highly restricted, discrete energy levels. The consequences of this quantum trap are just mind-bending. Because the electrons are confined, the actual optical properties of the material change. Take quantum dots, for example. These are basically tiny semiconductor nanocrystals. If you shine a light on them, they emit a color. But here is the really amazing part. If you simply change the physical size of the dot, say making that microscopic box just a tiny, tiny bit bigger or smaller, the color of the light it emits completely changes. A 3 nanometer dot might glow green, while a 5 nanometer dot of the exact same material glows red. No way, right? The physical size alone dictates its color? And it's not just light and color getting rewritten at the nanoscale. Let's do a quick rapid fire of some other weird stuff.
Mechanically speaking, things like carbon nanotubes reach an absolutely insane tensile strength of about 100 gigapascals. That is vastly stronger than steel. Magnetically, if you shrink magnetic particles below a certain critical size, they completely lose their permanent magnetism and become super paramagnetic, reacting to magnetic fields in entirely new ways. Thermally, a single atomic layer of carbon, which we call graphene, exhibits incredibly enhanced thermal conductivity. Basically, at the bottom, materials become super strong, superconductive, and highly malleable.
Section 4. Real-world nanomaterials. The invisible tech shaping our lives.
Now, you might be sitting there thinking, this all sounds like some abstract science fiction, right? But the truth is, this invisible engineering is already deeply anchored in our everyday reality. Remember that high surface reactivity we talked about? Well, that gives Nano-Silver incredible antimicrobial power, which is actively used in modern wound dressings. Or take Nano-Titanium dioxide. It acts as a photocatalyst, allowing modern building windows to literally clean themselves using just sunlight. Carbon nanotubes are out there being tested for advanced aerospace engineering right now. Graphene, it's officially the strongest material known to humanity. And those amazing color-changing quantum dots, they are the exact literal technology powering the ultra-vivid colors you see in modern television displays, as well as highly precise biological imaging in hospitals. This stuff is everywhere.
Section 5. How do we build them? The builder's dilemma.
Now, what's really interesting about this next concept is the absolute headache of figuring out how to build something that's a billionth of a meter small. How do you build the invisible? Well, scientists face a real dilemma here with two completely different philosophies. First, you've got the top-down approach. Think of a sculptor working with a giant block of marble. You start with bulk material and aggressively chisel it away using techniques like milling, etching, or lasers. It's great because it's scalable for mass production, but trying to use brute force to get below 10 nanometers, it's immensely difficult and takes a huge amount of energy. Conversely, we have the bottom-up approach. This is essentially like building with Lego bricks, but the bricks are individual atoms. By using complex chemistry, we can actually trigger atoms to self-assemble into nanostructures. It's incredibly precise, perfectly tailored, and gets us extremely small structures. But the catch? It's often much slower and significantly harder to produce on a massive industrial scale.
Honestly, this top-down, brute force method is really how we've traditionally tried to master materials. We take a giant block of familiar, stable bulk stuff, and we just aggressively chisel it down. We relentlessly break it apart, milling and etching it further and further, trying to force our way down until we finally breach that magical 100 nanometer threshold, where the rules of physics just flip completely upside down.
Which leaves us right here. We've just peered into a world where simply shrinking an object can completely change its color, drastically drop its melting point, and even turn it into the strongest material on Earth. But you know what the crazy truth is? This is just the very beginning of our descent into the microscopic. As we continue to really master the art of building our universe atom by atom, we have to step back and ask ourselves, what new, seemingly impossible rules of reality will we uncover next? Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.